Welcome to Haience, where humanity meets science. Tonight, we invite you to relax, perhaps close your eyes, and join us on an extraordinary journey to the very beginning of everything, the birth of the universe. We'll explore the Big Bang Theory, the scientific story of how our cosmos came to be, using simple ideas and relatable stories. So, find a comfortable spot, let your mind drift, and let's travel back 13.8 billion years to the dawn of time. The birth of the universe, a cosmic journey. Under a sky full of stars, have you ever wondered how everything began? In a poetic, meditative drift through time, we will journey back to the birth of the universe. A story written in light and darkness, chaos and calm. This narrative will use simple words and gentle imagery to explain actual scientific events, from the fiery beginnings of the cosmos to the emergence of the first stars. Imagine yourself relaxing, perhaps eyes closed, listening as the tale of 13.8 billion years unfolds. This is a story for students and science enthusiasts alike, meant to both inform and soothe, a cosmic lullaby of creation. We will start at the very beginning, as much as science can glimpse it, when time and space themselves were born. We'll explore how our universe expanded from something unimaginably small and hot into the vastness of. Today, along the way, you'll hear about the first light that ever shone, the long cosmic night that followed, and the dawn of the first stars and galaxies. Actual scientific milestones, like the formation of the first atoms and the blow of the cosmic microwave background, will guide our journey. But don't worry, we'll use easy-to-understand words, friendly examples, and a calm, story-like tone. So get comfortable. Let your mind drift among the stars. We are traveling back through eons, back to the moment of creation. In this gentle voyage, we'll witness the universe's birth and discover how it set the stage for everything, the galaxies, the planets, and even us. Our journey begins in darkness before the first dawn, a time before time itself. Before time began, the primordial void. Picture the universe before there was a universe, a difficult concept, since even time and space did not exist in the way we know them. In scientific terms, time zero, the very beginning, is a mysterious point beyond which we cannot currently see. It's often said that asking what happened before the beginning may not even make sense. Because time itself began with the birth of the universe. There was no before in the ordinary sense. There was no space out there waiting, no up or down, no yesterday to that first moment. At this primordial moment, all the matter and energy that would become our cosmos were squeezed into an unimaginably small point. You can think of it as an extremely dense seed, or a tiny singularity, where the laws of physics as we know them were stretched to their limits. It is hard to imagine everything, all galaxies, stars, atoms, and light, fitting into something smaller than a pinhead. Yet, according to the Big Bang Theory, this is our best understanding. The universe began in a state of infinite density and temperature. In that void before time, there was no light, no darkness, nothing at all in the conventional sense. Then, in an instant, something changed. We don't yet know what triggered it. Scientists have many ideas. But this is one of the great cosmic mysteries. What we do know is that about 13.8 billion years ago, the universe as we know it burst into existence. Space itself began to expand, carrying energy and matter with it. It's important to understand that this was not like an ordinary explosion with shrapnel flying into empty space. There was no outside space for it to explode into. Instead, space itself was stretching and expanding in all directions. Every part of space began rushing away from every other part. If you could somehow have been there, an odd thought, since there didn't exist until it happened, you wouldn't see a fireball expanding into space. Rather, space was ballooning outward everywhere at once. A common analogy is to imagine the universe as a balloon, with dots on it representing galaxies. In the beginning, the balloon was extremely small and tightly packed. Then the balloon started inflating rapidly. The dots galaxies too move apart, not because they are flying on their own, but because the surface of the balloon, space, is stretching. In the same way, the Big Bang was the expansion of space itself, not a conventional explosion. This expansion set the stage for the birth of the universe as we know it. At the exact first fraction of a second, conditions were beyond extreme. The infant universe was incredibly hot and dense, so hot that even the concept of atoms or particles as we know them didn't yet apply. All the forces of nature that now operate independently, gravity, electromagnetism, and the nuclear forces, were probably unified into a single force in those very first moments. Nature was perfectly symmetric and balanced in a way that is hard to fathom, and such a state was too symmetrical to last. Physicists theorized that as the universe began to expand and cool ever so slightly, this perfect symmetry broke. Gravity splits away first from the other forces. The strong nuclear force separated next, triggering an important event we'll discuss in a moment. Slowly, the familiar forces that govern our world emerged from the unified whole, like distinct threads unraveling from a tightly woven braid. For now, imagine that initial moment as a silent nothingness, poised on the brink of something. Then the cosmos took a breath, and the journey began. The first blinding moment, cosmic inflation. In the first instance after the birth of the universe, something truly extraordinary happened. The universe underwent a sudden burst of expansion called cosmic inflation. In less than a heartbeat of time, a tiny fraction of the second, the universe swelled enormously in size. How fast did it grow? Try to picture it. Scientists estimate that between about 10 to the power of negative 36 and 10 to the power of negative 32 seconds after the beginning, the universe expanded by a factor of at least 10 to the power of 26. That is, 100 million billion times bigger, effectively going from subatomic scale to perhaps the size of a grapefruit almost instantly. This astonishing inflation happened faster than the speed of light. That sounds impossible, but remember, it was space itself expanding. Einstein's speed limit applies to objects moving through space, not space expanding. No physical law was broken. Instead, this rapid growth is built into the fabric of the Big Bang story. What did this inflation accomplish? It took what was a tiny hot speck of universe and stretched it out enormously. In doing so, it smoothed and flattened the cosmos. Any irregularities or wrinkles were spread thin. Imagine taking a wrinkled balloon and inflating it hard. The surface flattens out as it expands. Similarly, cosmic inflation helped make the universe very smooth and almost uniform on large scales. Tiny random fluctuations, which were present even in that minuscule beginning, got blown up to macroscopic scales. These little density variations were like seeds. Later on, under the influence of gravity, those seeds would grow into galaxies and clusters of galaxies. In other words, inflation planted the subtle patterns that eventually became the cosmic web of galaxies spread across the universe. During this blink-of-an-eye expansion, the energy driving inflation was likely part of space itself, a high-energy field that suddenly released its energy as the inflation ended. When inflation came to a stop, all the tremendous energy that had caused space to expand didn't just vanish. Instead, it transformed into a hot, dense brew of particles and radiation. Essentially, this transformation is what we often think of as the Big Bang explosion. 15. In a process physicists call reheating, the vacuum energy of inflation converted into matter and light, flooding the young universe with the stuff that would eventually form everything we know. Let's pause and paint a mental picture. The time is now perhaps 1/trillionth of a second after the very beginning. The universe, once unimaginably tiny, has expanded to a more comfortably large size, though still far smaller than today. Of course, it is filled with a brilliant, searing fog of energy. Temperatures are mind-boggling. 3 easily in the range of 10 to the 27 to 10 to the 32 degrees Celsius in the earliest instance. All around, particles are erupting into existence from pure energy. Recall Einstein's E equals mc squared, which tells us energy can convert into matter. There are no atoms yet, not even protons or neutrons. Instead, the universe is a plasma of the most elementary constituents. Things like quarks, the building blocks of protons and neutrons, and leptons, like electrons, as well as their antimatter counterparts. Everything is moving and colliding at incomprehensible speeds. In these first flickers of time, the 4 fundamental forces of nature are starting to take their distinct roles. Gravity has already become its own force, shaping the overall expansion. The strong nuclear force has separated and will soon glue quarks together. The electromagnetic and weak nuclear forces are still merged for a little while longer in what physicists call the electroweak epoch. It's an exotic time that we can barely probe with modern physics. But we believe this is how our physical laws settled into place. Try to imagine it in a more human way. If the newborn universe were a story, this is the explosive opening chapter. High drama, incredibly fast-paced, over almost as soon as it began. From utter quiet, we suddenly have an inferno of creation, a tiny cosmos expanding and filling with light. It is blindingly bright, but there is no one to see it yet. The entire universe is like a hot, glowing soup, so dense and opaque that light itself is trapped, scattering from one particle to another. It's as if the universe is overcast by a brilliant fog, no clear sky anywhere. Just an intense glow permeating everything. Inflation was over in a flash, but its after effects set the course for everything to come. Now, with space swollen and energy converted into matter, the stage is set for the next act. The universe begins to cool and evolve. And the primordial soup of particles will start building the more familiar pieces of matter. A hot, cosmic soup, the first seconds and minutes. As the furious pace of inflation slowed, the universe entered a period of more gradual expansion. Though gradual is relative, as things were still changing on rapid timescales, we are now in the first second of the universe's existence. The temperature is still staggeringly high, on the order of 10 billion degrees Celsius, around 10 to the power of 10 billion degrees Celsius. That is about 1,000,000 times hotter than the core of our sun. At such temperatures, matter and energy are nearly indistinguishable. The cosmos is a roiling plasma of fundamental particles, quarks, which normally would combine into protons and neutrons, gluons, carriers of the strong force-binding quarks, electrons and positrons, the electron's antimatter twin, neutrinos, and a huge number of high-energy photons, particles of light. It's an extremely dense, hot fog of particles and radiation, truly a primordial soup. In these early moments, matter and antimatter were being created and destroyed in large quantities. Every particle that formed had its mirror opposite, its antiparticle, and when the two met, they annihilated each other in a burst of energy. You might think all matter would have been wiped out by these annihilations. In fact, scientists believe that almost all of it was, except for a tiny difference. Somehow, matter gained a slight edge over antimatter. For every billion matter-antimatter particle pairs that destroyed each other, perhaps one extra matter particle was left unpaired. That tiny surplus, just a 1 in a billion imbalance, meant that some matter remained when the mutual annihilation settled down. Everything we see today, every star, planet, and person, is made from those leftover matter particles. This is a profound fact. Had matter and antimatter been perfectly equal, they would have completely canceled out, and our universe would be nothing but light. But thanks to that small asymmetry, matter survived. The exact cause of this imbalance is still an unsolved mystery of physics, sometimes called the baryon asymmetry problem, but without it, we wouldn't be here to wonder about any of this. Within the first second, some important transitions occurred. As the universe cooled from its initially unimaginable temperature, it crossed thresholds where new kinds of particles could form or survive. By about a millionth of a second, 10 to the negative 6 seconds after the Big Bang, the temperature had fallen enough that quarks could start combining into composite particles called hadrons, like protons and neutrons. This moment, the end of the so-called quark epoch, is when quarks, which had been free, felt the strong force glue and locked together in threes to make protons and neutrons. This process is sometimes poetically called the universe's first quark knitting, weaving the first protons and neutrons out of the quark-gluon plasma. Any remaining quark-antiquark pairs that hadn't annihilated were now safely bound in these hadrons. By 1 second after the Big Bang, the universe was a little cooler, but still around 10 billion degrees Celsius or period. About 18 billion degrees Fahrenheit. At this point, it was full of particles of matter, protons, neutrons, electrons, and particles of light, photons, all chaotically bumping into each other. Neutrinos, ghostly particles that hardly interact with anything. Had already streamed free by this time, zipping through space never to interact much again, a cosmic neutrino background silently permeating space even today. The universe was still an opaque fireball of radiation and hot matter. If we could see it, it would appear as an intense white-hot glow, but in truth no eyes could survive to witness such a scene. Let's move a bit further forward in time, to a few minutes after the Big Bang. Now the universe has expanded and cooled enough to do something new, form the first atomic nuclei. This era is known as Big Bang nucleosynthesis, a term meaning building nuclei in the Big Bang. Around 3 minutes to 20 minutes after the beginning, the temperature fell to about 1 billion degrees, 10 to the power of 9 degrees Celsius. That's still incredibly hot, roughly 70 times hotter than the core of the sun. But it's cool enough that protons and neutrons can start to stick together without instantly being ripped apart. In this window of time, protons, which are just hydrogen nuclei, began fusing with neutrons to form the nuclei of helium. Nuclear reactions similar to those in stars were happening everywhere, all at once, in the thick primordial soup. The key products of this brief period of fusion were the light elements, mostly hydrogen and helium, with tiny traces of lithium, and a beryllium isotope that was unstable and quickly decayed. In fact, calculations and observations show that about 25% of the mass of the universe became helium in those first minutes, with the remaining 75% as hydrogen by mass. In terms of the number of atoms, hydrogen atoms vastly outnumber helium atoms, since helium is heavier. But by mass, it was roughly 3 to 1 hydrogen to helium. This is an important success of the Big Bang theory. It predicted this ratio before it was measured. And the observed abundances of primordial hydrogen and helium match the theory well. No heavier elements, like carbon, oxygen, iron, etc., could form yet. The universe had neither the right conditions nor the time for that. Elements heavier than lithium would have to wait billions of years until the first stars were born and cooked those elements in their cores. After about 5 minutes, the universe had cooled too much for further fusion. The nucleosynthesis era ended. At that point, the composition was set: about 75% hydrogen, 25% helium, with a dash of lithium, a mix that remains largely the same in the universe today, except in regions where stars have processed the raw material. Essentially, the whole universe during those minutes acted like a giant nuclear reactor, forging the light nuclei everywhere. And then, as expansion continued, the furnace switched off. No more new nuclei would form naturally until stars ignited. Much later. So, by the time we reach, say, 15 to 20 minutes after the Big Bang, the universe has become a bit less chaotic. It's still extremely hot, hundreds of millions of degrees and cooling, and it's still a glowing plasma. A hot sea of nuclei, electrons, and photons. But now the types of particles have reduced. We have a lot of hydrogen nuclei, protons, some helium nuclei, each composed of 2 protons and 2 neutrons, a few lithium nuclei. A sea of electrons roaming free, and an immense number of photons, light particles, scattered about. The photons are still energetically interacting with charged particles, electrons and nuclei, constantly scattering off them. This means light cannot travel far without bumping into something. The universe is like an extremely dense fog of glowing plasma. Just as you can't see far in a fog because light bounces off water droplets, you couldn't see through the young universe 5 because light was scattering off electrons incessantly. NASA scientists often compare it to the way sunlight scatters in a cloud, making the cloud opaque. In this early time, if there were an imaginary observer, they would be blinded by a bright haze everywhere. No stars, no structures, just a brilliant, featureless light permeating everything. The universe at this point was radiation-dominated, meaning most of the energy was carried by photons. Matter, the nuclei and electrons, was present, but the photons were so abundant and energetic that they dominated the dynamics. However, as expansion went on, the photons lost energy, their wavelengths stretched with the expanding space, and the universe kept cooling. Eventually, the balance of power would tip. Matter would come to dominate over radiation. That milestone happened a bit later, roughly 50,000 years after the Big Bang. The matter-dominated era began, but it was still far in the future from our current point of a few minutes post-Big Bang. For now, let's summarize this epoch in gentler terms. In the first few minutes, the universe grew from a blazing concoction of fundamental particles into a still blazing, but more familiar soup of protons, neutrons, and electrons. It created the first chemical ingredients, hydrogen, helium, lithium, that would later form stars and galaxies. The young cosmos is glowing white-hot, but like a sun wrapped in fog. The light is trapped. If you were floating in a small bubble within this plasma, again, a purely imaginary scenario, you'd be surrounded by a uniform brilliance. There would be no sense of up or down. No stars to punctuate the light, just a searing brightness and heat in all directions. It was an intense and active time, but in a way, much of the action was over quickly. The universe had accomplished an incredible amount in its first few moments. More, perhaps, than it would in billions of years to follow. As the clock ticks onward, things are slowing and cooling, setting the stage for a profound transformation, the emergence of the first light that could freely shine across space. Let there be light, the first atoms and afterglow. For thousands of years after those first minutes, the universe remained a hot, opaque plasma. Although nuclei of atoms had formed, the searing temperatures, millions of degrees, meant that electrons were still too energetic to settle down with nuclei. Any time an electron tried to combine with a nucleus to form a neutral atom, a high-energy photon would immediately knock it loose. The cosmos was essentially an ionized gas, a fluid of positively charged nuclei and free electrons. Imagine a vast cloud of charged particles with light continually scattering off them. This was the state of the universe for hundreds of thousands of years after the Big Bang. As expansion continued, however, the temperature kept dropping. From millions of degrees, it fell to hundreds of thousands, then to tens of thousands. The intense light, photons, also lost energy as wavelengths stretched out. The once blinding white-hot glow shifted toward cooler colors, from white to yellow to red, as the universe expanded and aged. The term aged is relative here because we're talking tens of thousands of years old, which is infancy on a cosmic timescale. Finally, approximately 380,000 years after the Big Bang, a critical threshold was reached. The universe cooled to about 3,000 K, around 2,700 degrees Celsius, which is roughly the surface temperature of a red-orange star like our Sun. At around this temperature, electrons can at last combine with nuclei and stay attached. Hydrogen atoms formed when electrons settled into orbit around protons. Helium atoms formed as electrons joined helium nuclei. This epoch is aptly named recombination. Even though it's the first combination of electrons and nuclei, the term stuck historically. What is so special about recombination? Two major things happened that completely changed the nature of the universe. First, with electrons bound into atoms, they were no longer free to scatter every photon that comes by. The cosmic fog lifted. All of a sudden, space went from opaque to transparent. Photons that had been endlessly ricocheting around were now free to travel in straight lines. It is as if the universe took off a heavy veil and became clear. For the first time in cosmic history, light could travel unimpeded across significant distances. Second, the very act of all those electrons dropping into atomic orbits released energy in the form of new photons. The newly formed hydrogen and helium atoms emitted a gentle afterglow of light as they transitioned into stable states. And since suddenly photons were free to go, that light rushed out across the universe. This released radiation, combined with the primordial light that was already present but now unleashed, is what we today call the cosmic microwave background, CMB. At the moment of recombination, it would have been a bright flash of light everywhere, marking the universe's first light. Over billions of years, that light has stretched into microwaves due to the ongoing expansion. But we can still detect it around us as a faint glow coming from all directions. It is often described as the afterglow of the Big Bang. The oldest light we can see in the universe. Imagine this moment from a poetic angle. After a long period of intense heat and blinding haze, the universe suddenly becomes transparent. If you were an observer at the time, you would witness the entire sky light up and clear out at once. One instant, everything is an opaque glow around you. The next instant, that glow floods outward and you could in theory see through space for the first time. The light released at that time would have been a warm color, around 3000 K, likely a yellow-orange-white hue, similar to the warm light of an early evening sun. It bathed the newborn atoms in a gentle radiance. As time went on, this light stretched to longer wavelengths, turning to red, then infrared, then microwave, and dimmed, but it never disappeared. Today, the cosmic microwave background is a very cold 2.7 Kelvin, negative 270 degrees Celsius, because of the expansion of the universe, but is essentially the fossil light from that moment when the universe first became transparent. Let's put into context how significant this event was. The moment of recombination and photon decoupling. Meaning photons decoupling from matter and flying free is sometimes poetically likened to the universe taking its first breath or first light. In religious or artistic metaphors, one might say, "Let there be light." And here we have the scientific version of that moment. After recombination, the universe was filled with light that could finally travel. If there had been eyes to see, the entire cosmos would be aglow with a bright fog that quickly thinned into darkness. As light raced away, but note, it quickly thinned into darkness. Why? Because once the light streamed out, the source, the hot plasma, was gone, turned into neutral gas. After the flash of recombination, there were no stars yet to shine. So after this first light was emitted, the universe actually entered a dark age. The photons from recombination kept traveling, getting redder and less energetic, effectively dimming down as the universe expanded. Beyond that afterglow, there were no new light sources on the scene for quite some time. What was left behind was a transparent universe filled mostly with hydrogen and helium gas. The gas itself was not glowing, not much anyway after that initial release, and space was clear. If you imagine being somewhere in the universe a few million years after recombination, it would be a lonely view, darkness all around. Perhaps a faint warm glow from the receding CMB if you had infrared eyes, but no stars, no galaxies, just the cold gas and the dim relic radiation. This period is aptly called the Cosmic Dark Ages. Before we move on, let's recap gently. Around 380,000 years after its fiery birth, the universe cooled enough to form the first atoms. With electrons happily bound in orbits, the omnipresent light was set free, and the universe went from a brilliant opaque glow to a vast transparent darkness. The light released at that time still surrounds us as a faint microwave signal, a whisper from the infant cosmos. The stage was now set for the next chapter. The emergence of structure, of stars and galaxies, but at this moment, the universe was like a dark, silent canvas. 7. The ingredients were all there, mostly hydrogen gas, spread out and cooling, with a mysterious ingredient called dark matter, more on that soon, also present throughout space. But there were no lights in the sky yet. For perhaps 100 million years or more, the cosmos would remain dark as gravity slowly worked on the primordial gas, preparing the first sparks of starlight. One might say the universe had its first light and its first sunset, setting the stage for a cosmic dawn to come. The Cosmic Dark Ages, darkness before the dawn. With the afterglow of the Big Bang fading into the background, the universe entered a long period of darkness. Picture a vast expanse of space filled with hydrogen and helium gas, but no stars to illuminate the void. This era, often called the Cosmic Dark Ages, lasted from about 380,000 years after the Big Bang until the first stars ignited, perhaps around 100 to 200 million years later. During this time, the universe was transparent but unlit. The night after the first day, so to speak. What was happening in this darkness? On the face of it, not much visible. However, quietly, gravity was at work. Remember those tiny irregularities, the slightly denser spots that were stretched out by inflation? Those spots are crucial now. Even a minuscule extra density of matter in one region meant a tiny gravitational pull above average. Over time, these denser pockets of gas began to attract more matter from their surroundings. It's a slow process, but gravity is persistent. The denser got denser, the sparse got sparser, a case of the rich get richer in terms of mass distribution. These gathering clouds of gas were the seeds of future stars and galaxies. Here we should introduce a key player in the cosmic story: dark matter. Dark matter is a form of matter we cannot see with any telescope because it doesn't emit or absorb light, but it has gravity. In fact, dark matter makes up the majority of the matter in the universe, about 85% of the total matter content. During the Dark Ages, dark matter had already started to clump even earlier than ordinary gas. Because dark matter feels gravity but was not coupled to light at all, it wasn't stuck in the plasma in the same way. So while the normal matter, hydrogen-helium gas, was just beginning to fall into clumps, dark matter had formed an invisible framework of overdensities, a kind of cosmic scaffolding of massive clumps and filaments. This dark matter scaffolding helped pull the ordinary gas into clouds along its structures. You can imagine dark matter as an invisible web, and along that web, the first gas clouds started to collect in nodes and strands. Without dark matter's head start and extra gravity, the gas alone might have taken even longer to form stars. Throughout cosmic history, dark matter has been the quiet architect of structure, gathering matter and guiding the formation of galaxies. So during the Dark Ages, in the dark matter halos and filaments, the primordial gas was pooling. These were still dark, cold clouds, though cold is relative. Initially, they might be hundreds or thousands of degrees, but cooling progressively. There were no bright objects yet. But if we could somehow have superhuman senses, we'd notice matter slowly moving, falling into deeper pockets. As these gas clouds contracted under gravity, their centers grew denser and hotter. Think of how compressing air in a bike pump makes it warm. Compressing gas in a huge protostellar cloud raises the temperature. It took tens of millions of years, but eventually some of these gathering clouds got dense and hot enough in their cores for a drastic change. Nuclear fusion ignited. This is the defining moment for a cloud of gas to become a star. Now we come to the cosmic dawn, the end of the Dark Ages, when the first stars turned on. Exactly when the very first star ignited is not known precisely. It could be around 100 million years after the Big Bang, or 150 million, or maybe a bit more based on the latest research. Recent observations by powerful telescopes like JWST, James Webb Space Telescope, hint that significant star formation was underway by 200 million years or so after the Big Bang, possibly even earlier. But let's paint it broadly, by around 150 to 200 million years post-Big Bang. The universe is no longer utterly dark. Scattered in the vast darkness, brilliant blue-white stars begin to shine. These first stars, often called population 3 stars by astronomers, were unlike the stars we see today. They formed out of pure hydrogen and helium gas, with virtually no heavier elements because no stars had lived and died yet to create those elements. This chemical simplicity, along with the conditions of their birth, next, likely made them very massive. Studies suggest many of these first stars were tens or even 100 times more massive than our Sun. The NASA history we saw noted they could be 30 to 300 times the Sun's mass. And the physics timeline said around 100 times the Sun. Imagine enormous stars, extremely hot and bright, pouring out light into the darkness. These stars burned bright blue-white because very massive stars are hotter and bluer in color. They were also short-lived in cosmic terms. A star dozens of times the Sun's mass might burn out in only a few million years. But while they lived, they shone millions of times brighter than our Sun. Let's linger on this moment. After ages of darkness, points of starlight pierce the cosmic night. It must have been a glorious sight for hypothetical observers. The first stars lighting up like a million tiny candles in a pitch-black hall. Of course, these stars were likely not isolated. They formed in clusters or groups within the same cloud. So one might see a whole cluster of newborn stars lighting up together, perhaps forming the core of what will become a proto-galaxy. With the birth of the first stars, the universe experienced a second kind of illumination. The Dark Ages were ending, and what some call the cosmic dawn had arrived. The universe had gone from darkness to being dotted with brilliant starry islands. Now, what were the implications of these first stars? Enormous. For one, their light began to transform the environment around them. The space between stars was filled with neutral hydrogen gas, which, as we noted, is transparent to visible light, but can absorb high-energy ultraviolet UV light. The first stars emitted a lot of UV radiation because they were so hot. This UV radiation started to ionize the hydrogen gas once again, meaning it would strip electrons off hydrogen atoms, turning them back into protons and free electrons. This process is called reionization, since the gas had been ionized in the early universe, became neutral at recombination, and now was ionized again by starlight. At first, each star, or cluster of stars, was surrounded by a bubble of ionized gas amid the neutral gas. But as more and more stars formed, these ionized bubbles grew and merged. Over a few 100 million years, approximately between 150 million and 1 billion years after the Big Bang, the universe went from mostly neutral back to mostly ionized. By about 1 billion years after the Big Bang, the intergalactic medium, the stuff between galaxies, had been largely reionized, the fog of neutral hydrogen cleared by the fierce ultraviolet glare of early stars and galaxies. This era of reionization is complex and an area of active research. But what it means simply is that the universe became transparent to ultraviolet light as well, not just visible light. The fog of neutral hydrogen that could block UV was burned away by the first generations of stars and quasars, very bright young galaxies. After reionization, light could travel freely across the cosmos at all wavelengths, as it does today, unless blocked locally by pockets of gas or dust. While reionization was happening, the first galaxies were also taking shape. Gravity, working on both dark matter and ordinary matter, caused stars to cluster into galaxies. The first stars likely formed in small protogalactic clumps. Think of them as the seeds of galaxies. These clumps merged or attracted more gas and stars, building larger structures. Over several 100 million years, the first small galaxies formed, and then those merged into larger galaxies, and so on. We believe that by around 500 million to 1 billion years after the Big Bang, galaxies of significant size, though smaller than our current giant galaxies, were common. The universe was no longer a uniform expanse of gas. It was a tapestry of stars, star clusters, and young galaxies, all amidst an ever-thinning neutral gas background. As this cosmic dawn progressed, the universe began to resemble a stellar ecosystem. The massive population 3 stars lived short lives and died spectacularly, likely as supernovae or perhaps even more exotic explosions like hypernova or direct collapses to black holes. When they died, they spewed their ashes, that is, heavy elements they created via nuclear fusion, into the surrounding space. For the first time, elements like carbon, oxygen, nitrogen, silicon, iron, the stuff that makes up planets and people, were being created in quantity and distributed into space. The next generations of stars, population 2, later population 1, which includes our Sun, would inherit this material. This means each generation of stars had more metals, astronomers speak, for elements heavier than helium than the previous. The cosmic chemical enrichment had begun with the deaths of the first stars. To give an analogy, the early universe had only hydrogen and helium, like a very simple toy box with just 2 kinds of blocks. The first stars were built from those blocks alone. But those stars, through their lives and explosive deaths, created new types of blocks and scattered them around. Now the toy box, the interstellar medium, had many more boxes, kinds of blocks, and new stars could be built with a richer variety of materials. Eventually, this allows things like planets to form, since you need elements like iron, silicon, oxygen for rocks, and so on, which the first stars' furnaces provided. Back to our narrative, by about 1 billion years after the Big Bang, the universe was brimming with galaxies, some small, some growing larger through mergers. The cosmic web of large-scale structure had become pronounced. Filaments of matter, with galaxies embedded, and great voids in between, much like we observe today on large scales. The dark matter, which had guided this structure formation, continued to pull galaxies into clusters and superclusters. The universe was still smaller and denser than it is now, and galaxies were closer together back then, often colliding and merging more frequently. It was a very dynamic, active universe. From the end of the Dark Ages onward, there was light again, starlight, in the universe. The sky would have been populated with stars and galaxies if there were eyes to see. Over the next billions of years, stars would continue to form and die. Galaxies would grow, sometimes form majestic spirals or gigantic ellipticals. Clusters of galaxies would form, and the expansion of the universe would carry galaxies farther apart. It was an era of evolution and maturation for the cosmos. Let's imagine ourselves drifting through this epoch. We pass into a newborn galaxy, feeling the warmth of countless hot blue stars that have recently ignited. Massive stars explode like cosmic fireworks here and there, stirring the surrounding nebulae with shockwaves and seeding heavy elements around. New stars take birth from the enriched gas clouds, more moderate stars, maybe with planets forming in disks around them from the newly available ingredients. The once pristine hydrogen-helium universe is now diversified with the colors and chemistry of stardust. Among these later generations of stars, in the quiet arm of a spiral galaxy, our own sun would eventually form, but that's still far in the future from the 1 billion year mark. For now, we marvel at the transformation. From a dark, simple universe of only gas, we now have a universe filled with wonders, bright stars, glowing nebulae, spinning galaxies. The cosmos has awakened. From stardust to us, the cosmic connection. As time marched on, the universe continued to expand and evolve. Stars and galaxies became the main features of the cosmos. Let's fast forward through cosmic history, keeping our calm, meditative pace to see how the universe's birth eventually led to us. By around 5 billion years after the Big Bang, large galaxies like our own Milky Way had formed. The Milky Way likely started as smaller proto-galaxies that merged. It became a grand spiral galaxy with billions of stars. Generations of stars lived and died in its disk, enriching the gas further with heavy elements. About 8.5 to 9 billion years after the Big Bang, which corresponds to roughly 4.5 billion years ago from today, a new star was born in one of the Milky Way's spiral arms. This star was modest in size, not a massive blue giant, but a medium yellow star. It's our Sun. Our Sun is described as a late-generation star, meaning it formed after many generations of stars had already come and gone in our galaxy. It was born from a cloud that contained the ashes of countless supernovae before it. Those ashes, heavy elements, allowed something special to form around the Sun: planets. In the rotating disk of gas and dust around the young Sun, planets coalesced. Among them was a small rocky world at just the right distance for liquid water, Earth. Earth inherited carbon, oxygen, iron, silicon, all the elements forged by stars over the prior billions of years. Indeed, the atoms in our Earth and in our bodies were literally made in stars that died before the Sun was born. The calcium in your bones, the iron in your blood, the oxygen you breathe, none of those were made in the Big Bang. The Big Bang made hydrogen, which is a big part of our water and our bodies too, and helium, not much in us, but in the Sun. But carbon, nitrogen, phosphorus, and so on were synthesized in stellar furnaces. We truly are made of star stuff, as the famous saying goes. It's not just poetic. It's scientifically true that the elements of life were forged in stars. On Earth, life eventually emerged by about 10 billion years after the Big Bang. Life was flourishing on our planet, which corresponds to approximately 3.8 billion years ago. Life is a topic for another time, but it is incredible to realize that we are a part of this cosmic story. The universe gave birth to stars. Stars seeded planets, and on at least one of those planets, beings arose who can contemplate it all. We are a way for the universe to know itself, as Carl Sagan mused. Now, as we reach the present day, about 13.8 billion years since the beginning, we find ourselves gazing out at the cosmos with wonder. The night sky that soothes us is filled with the faint light of countless stars and galaxies. When you look up on a clear night away from city lights and see the Milky Way's band, you are looking into the past, seeing light that may have left its source thousands of years ago. With telescopes, we can see galaxies billions of light years away, which means we are seeing them as they were billions of years ago. And some even in their youth, not long after the cosmic dawn. In a sense, the universe's past is still visible to us because light takes time to travel. The cosmic microwave background, that first light from recombination, is observed today as a faint microwave signal across the sky. We have satellites that have mapped it, revealing a very slight modeling, those tiny fluctuations that eventually led to galaxies. It's like seeing a baby picture of the universe. 4. A snapshot of the fireball long ago. It's amazing that our scientific instruments allow us to piece together this story from such evidence. Finally, before we conclude our journey, let's talk about the present and future in a calm tone. The universe continues to expand. In fact, to our surprise, the expansion is accelerating now due to a mysterious influence we call dark energy. In 1998, astronomers observed distant exploding stars, supernovae, and found they were fainter than expected, indicating that those galaxies are farther away than they would be if expansion were slowing. Instead, expansion had sped up. It appears an unknown force or energy inherent to space, dark energy, is pushing the universe outward faster and faster. If this continues, our universe will keep expanding forever, growing ever colder and more diffuse. Trillions of years in the future, stars will eventually burn out faster than new ones form. The night sky will slowly darken over unimaginably long timescales. But that fate is an extremely distant concern. For billions of years to come, there will still be stars being born, galaxies shining, and perhaps life thriving. As of now, our universe is comfortable middle-aged by some measures. Galaxies are active, new stars are still forming, including in our Milky Way, and we humans have the privilege of existing at a time when the sky is still rich with stars to see. Let's reflect on the journey we've taken. We went from nothingness, or at least nothing we can comprehend, to a blinding Big Bang expansion, to a hot, youthful universe full of plasma, to the release of the first light, and then a long darkness, into which the first stars ignited, bringing light and structure. From that came galaxies, planets, and eventually us, observers capable of retracing this story. It's a breathtaking cosmic tale. Through this whole narrative, we've maintained a gentle, flowing tone. You might almost imagine the universe itself as a living thing with a life cycle, born in fire, maturing with stars as its cells, and continuing to evolve. And though the scale is almost impossible to truly grasp, there is a reassuring continuity to it. The same physical laws that operate in your room right now were at play in the first seconds of the universe, and will be at play in the far future. We are intimately connected to the cosmos. In a very literal sense, we are children of the universe. Every atom in your body was forged either in the Big Bang, hydrogen, or in a star, the rest. We belong here as natural outcomes of cosmic processes. Conclusion. Our journey, a meditation on the birth of the universe, is drawing to a close. We began in darkness and silence before time and watched a flurry of creation. The Big Bang's expansion, the glowing primordial soup, the first atoms bringing forth light, the long cosmic night, and the dawn of stars. We saw how from the simplest elements came complex galaxies. How stars gave us the elements of life. We followed the universe through its baby steps to its stellar adolescence and into the present day. Take a moment to appreciate the grand timeline we've traversed in over an hour of contemplation. 13.8 billion years of history, from that initial singular event to the rich cosmos around us. In our mind's eye, we witnessed the entire life of the universe so far compressed into a peaceful narrative. If you are listening to this while trying to fall asleep, perhaps you feel a sense of calm insignificance, not a threatening insignificance, but a comforting one. The problems of our daily lives may seem a little smaller against the backdrop of cosmic history. The atoms in your body have seen the inside of stars and the beginnings of time. You are a part of this magnificent story. In the grand scheme, we are all stardust, uniquely organized for a brief moment, experiencing the universe, Above you, the stars you see, if you peek out your window or recall them from memory, are distant suns many light years away. Their gentle twinkle is a reminder of the enduring processes that began at the universe's birth. The very photons hitting your eye on a starlit night might have been traveling for hundreds or thousands of years before meeting you. And the cosmic microwave background radiation, the afterglow of creation, bathes you unseen. A very faint whisper from 13.8 billion years ago, now cooled and stretched, but still here. As you drift into sleep, imagine that you are floating through space and time. Feel the connection to the cosmos. Perhaps you drift past a newborn star, lighting up a nebula with soft colors, or glide through a galaxy like a lazy river of light, or back further to see the first star ignite in the dark. All those scenes are part of reality's tapestry. The universe is vast and ancient, yet here you are, a child of the stars, able to reflect on it. The story of the birth of the universe is both scientific and deeply poetic. It's written in equations and observations, but also in the inspiration it gives us. In a meditative tone, we have recounted scientific events, each supported by decades of research. Yet, the awe they inspire is like poetry for the soul. So, the next time you feel the weight of the world, perhaps step outside on a clear night. Look up. Remember that you are connected to the very first light that ever shone and to the very first particles that formed. The universe 12 began in a single blazing moment. And now, billions of years later, a part of it is listening to a story about itself. How wonderful is that? Thank you for coming along on this tranquil journey through the cosmos. The universe's birth is the ultimate origin story, and it continues to unfold with every passing moment. As you close your eyes now, imagine the gentle lullaby of the cosmos, the background hum of the Big Bang's afterglow, the distant songs of early stars, the quiet expansion carrying galaxies farther apart. Let that vast timescale and grand perspective calm you. In the great span of cosmic time, all is as it should be. Sleep well, dear listener, cradled by the knowledge that you carry a piece of the universe's birth within you.